Welcome, everyone. Today, we are focusing on a highly advanced topic, managing distributed training for large and deep learning models. Please note that while I will draw heavily on our Azure Machine Learning sources regarding pipelines, MFlow, sweep jobs, and compute environments, the specific mechanics of distributed deep learning frameworks such as data and model parallelism are industry-standard concepts from outside our provided sources, and you may want to independently verify those specific framework details. Let's get started. Let us kick things off by defining what distributed training actually is. When you are dealing with massive deep learning models, training on a single machine is no longer viable. Distributed training is the process of splitting that workload across multiple processors or compute nodes. The basics are simple. Instead of waiting weeks for one GPU to process your data, you harness a cluster of GPUs working simultaneously to finish in hours. Why is this mandatory today? Because modern deep learning architectures and their datasets literally exceed the physical memory and processing constraints of any single machine. How do we achieve this? We utilize cloud-based compute clusters that scale out horizontally. In our deep dive, we recognize that orchestrating this is complex. It is not just about raw power, it is about synchronizing gradients and managing node-to-node communication seamlessly so the cluster acts as a single, unified brain. Take a look at this flowchart to visualize the orchestration process. At the top, we start with our massive dataset and deep learning model. This flows into the distributed orchestrator. Instead of funneling all that data into one bottleneck, the orchestrator divides the workload, routing it to compute node 1, node 2, all the way to node n in parallel. As these nodes independently process their data batches, they must constantly communicate. Notice the dotted lines leading to the synchronize wait step. This represents the back-and-forth communication required to ensure all nodes are learning the same patterns. Finally, these synchronized insights converge to produce a single, highly accurate final deep learning model at the bottom. To physically run distributed training, we need an engine, and that engine is the Azure Machine Learning Compute Cluster. By definition, these are dynamic, multi-node compute targets engineered for distributed workloads. The basics involve provisioning a cluster that can automatically scale out to multiple virtual machines or nodes to execute your parallel tasks. Why do we use managed clusters instead of static servers? For cost optimization and scale. You can allocate massive GPU arrays for the duration of your training, and the cluster will automatically spin down to 0 nodes when the job is done. How do you implement this? You simply define the compute target in your Azure ML workspace and assign it to your training script. Diving deeper, the cluster isn't just a collection of computers. It provides the secure, high-bandwidth network topology required for those nodes to pass gigabytes of gradient updates back and forth without latency bottlenecks. This diagram illustrates the infrastructure behind our distributed setup. It begins with the training job request entering the Azure ML workspace. The workspace intelligently provisions the GPU compute cluster on demand. Look inside the cluster network box. The cluster has expanded into multiple GPU nodes. Crucially, notice the two-way arrows labeled high-speed interconnect between the nodes. In distributed deep learning, nodes must constantly share their learnings. This high-speed networking is what prevents the communication overhead from slowing down the actual training process, ensuring linear scaling of your computational power. Now, let us dive into the actual mechanics of how deep learning is distributed: data parallelism versus model parallelism. Keep in mind that while Azure handles the infrastructure, these specific parallelism frameworks are industry standards from outside our core documentation. Data parallelism is the most common. Here, you copy the exact same model to every single node, but you split your massive dataset into chunks. Each node trains on a different chunk of data simultaneously. You use this to drastically speed up training time. On the other hand, model parallelism is used when your neural network is so massive, like a billion-parameter language model, that it cannot physically fit into the VRAM of a single GPU. Here, you split the actual layers of the model across different nodes. How do you implement this? You use specialized libraries like PyTorch DDP or DeepSpeed within your training script, and Azure ML's compute clusters execute them flawlessly. This visual clearly contrasts the two dominant distributed strategies. On the left, data parallelism shows identical copies of the model copy A and copy B. However, they are being fed different chunks of data. They learn independently and then average their results. On the right, model parallelism shows the opposite. The full dataset is present, but the model itself is fractured. Model layers 1 through 5 sit on one node, while layers 6 through 10 sit on another. The data must flow sequentially through these nodes. Understanding this difference is vital for a machine learning engineer, as it dictates exactly how you will write your training scripts before deploying them to the Azure cluster. To manage the complexity of distributed training, we must orchestrate our workflows using Azure ML pipelines and components. As our sources define, a pipeline is a workflow of machine learning tasks where each individual task is encapsulated as a reusable component. The basics involve arranging these components either sequentially or in parallel. Why is this necessary for deep learning? Because preparing terabytes of data for distributed training is a massive job on its own. By using pipelines, we completely decouple the data preparation logic from the distributed training script. How do we do this? We use the pipeline Python function to stitch these components together. The true deep dive advantage here is hardware targeting. Because each component is independent, you can execute your data prep component on a cost-effective CPU cluster and then automatically route the pre-processed data output to your expensive, multi-node GPU cluster exclusively for the distributed training phase. Let us trace the execution of a pipeline. We begin with raw data entering component 1, which handles data prep. This component is likely running on a standard CPU cluster to save costs. Once complete, notice the transition arrow. The pipeline automatically routes the prep data outputs directly into the input of component 2. Component 2 is our heavy-duty distributed train component, running across our GPU cluster. Finally, component 2 outputs the fully trained deep learning model. This pipeline acts as an automated orchestrator, ensuring that massive distributed jobs run seamlessly from raw data to finished model without manual human intervention. Even with distributed training, your deep learning model will fail if its hyperparameters are wrong. To manage this at scale, we use sweep jobs for hyperparameter tuning. What is a sweep job? It is an automated process that searches through different configurations to find the optimal setup. The basics require you to define a search space, pick a sampling method, and configure early termination. Why do we need this? Because deep learning models rely on complex variables like learning rates and batch sizes. Guessing these manually across a distributed cluster wastes time and money. How it works is brilliant. The sweep job initiates multiple training trials in parallel across your compute nodes. Our deep dive focuses on early termination. When you are running massive distributed jobs, you are burning compute budget. Early termination actively monitors these parallel trials and automatically kills any trial that is underperforming, ensuring your cluster only spends time processing the most promising models. This flowchart maps out a distributed sweep job. The orchestrator at the top applies your search space and sampling rules. It then fans out, launching parallel trials 1, 2, and 3 simultaneously across your compute cluster. As these distributed trials run, their metrics constantly feed into the early termination policy node in the center. The policy acts as a ruthless judge. If trial 2 is underperforming compared to historical baselines, it routes to kill trial, freeing up those GPU nodes instantly. The surviving, optimal trials continue until completion, resulting in the best possible model being logged. This is how you optimize deep learning efficiently. When you distribute training across dozens of nodes, how do you keep track of the results? You configure MFlow for model tracking. MFlow is deeply integrated into Azure Machine Learning to track experiments. The basics are highly effective. MFlow acts as a centralized server that logs every hyperparameter, performance metric, and artifact generated by your runs. Why is this indispensable? Because if you have 50 parallel nodes training a deep learning model, you cannot manually parse 50 different log files to figure out your loss rates. You need centralized aggregation. How do you implement it? You simply add the mflow.autolog command to your Python training script. The deep dive benefit here is comparability. MFlow gives you a unified dashboard to compare the performance of all your parallel sweep job trials side by side, allowing you to definitively identify and register the best performing deep learning model. Look at how MFlow simplifies distributed chaos. We have our various compute nodes on the left: node 1, node 2, and node n. As they execute their distributed training loops, they all simultaneously stream their loss rates and metrics into the central MFlow tracking server. MFlow digests this incoming stream and organizes it into the aggregate dashboard. From this single pane of glass, a data scientist can effortlessly compare the parallel trials and monitor the overall health of the distributed deep learning experiment in real time. To manage distributed training in an enterprise, you cannot rely on manual clicks. You must automate the workflow. We do this by triggering Azure Machine Learning jobs with GitHub Actions. The basics involve shifting from manual notebooks to a robust, feature-based CI/CD pipeline. Why is automation critical? Because an effective MLOps strategy requires rapid, reliable delivery of artifacts. Manually configuring and launching a 100-node distributed training job invites catastrophic human error. How do we solve this? We store our Azure credentials securely in GitHub secrets and write a YAML workflow that triggers the pipeline job automatically when code is updated. Diving deeper into security, we implement strict branch protection rules. Data scientists must use feature branches. They cannot push code directly to main. This guarantees that all distributed training code is peer-reviewed before it ever spins up expensive compute clusters. This sequence diagram maps the automated MLOps workflow. It starts when the data scientist merges a peer-reviewed pull request in GitHub. This event acts as the trigger for GitHub Actions. The action securely retrieves the Azure credentials from GitHub secrets, ensuring no passwords are in the code. It then authenticates and commands the Azure ML workspace to trigger our massive distributed pipeline job. The workspace takes over, spinning up the compute cluster, and directly streams the MLflow logs back to the team. The entire distributed run is orchestrated securely and automatically. Let us tie everything together with a real-time use case. Imagine you are a machine learning engineer at Prosware, a healthcare startup. Your team is developing a massive deep learning classification model to diagnose diseases based on medical imaging. The basics: your dataset is terabytes of high-resolution scans, and the neural network is incredibly deep. The why: if you attempt to train this on a single workstation, it will take weeks, delaying critical application updates that practitioners rely on. The how: you architect a distributed solution. You build an Azure ML pipeline that utilizes a sweep job to distribute parallel training trials across a massive GPU compute cluster. The result: by orchestrating this with automated GitHub Actions and utilizing MLflow to track the best results, Prosware reduces training time from weeks to hours. They achieve a scalable MLOps lifecycle that continuously and safely delivers life-saving AI to the healthcare industry. Our final flowchart visualizes the complete Prosware solution. High-resolution medical imaging data enters the system. A code update triggers the GitHub Actions CI/CD pipeline, which launches the Azure ML pipeline. The pipeline efficiently routes data through the data prep component and then fans out into the distributed train component. Notice how the training workload is split across multiple GPU nodes simultaneously. All nodes feed their accuracy metrics back into MLflow to identify the ultimate winner. Finally, the optimized model is deployed to the practitioner app. This is the power of managing distributed training at enterprise scale.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by Quicktechie. So we have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material. So this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see this is all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper. It would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepared for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.